Okay, so for today's lecture, we're going to be focusing on basic structures, functions part 2. And in this set, we're going to take a look at some important functions as well as some applications of functions to computer science. So the first important function that we're going to take a look at is the floor function. And perhaps you've already worked with this in the past for some of your other classes, but it's basically defined as follows. We're going to take elements x from the set of real numbers and elements n from the set of integers. And then the floor function is defined to be, first of all, it's denoted with the floor is denoted with these kind of incomplete brackets. So that's read as the floor of x is equal to n, to integer n, where x is bound above by n plus 1 and bounded below by n, with the possibility that x might actually be the integer n. So what that means is that if you think about it on the number line, if n is an integer and n plus 1 is the next integer, that x is found somewhere in between those two integers. Just my highlighters real quick. So x is found somewhere in this interval with the possibility that it might be n. So another way to think of the floor function is to just think about it as rounding down regardless of what your decimal part is. So if you have like a 2.1, you would round down to 2. If you have a 2.7, you would round out to 2. So that's the floor function. And here are some examples that we're going to address. They're asking us to compute the floor function for the following values of a. So if I want to find out what the floor of 2.1 would be, that would be simply 2, because 2 is, and here's another part of the definition that I should have mentioned up here, but we could read n as being the largest integer that bounds x below, excuse me. And so I'm just going to write this as part of the definition. N is the largest integer that is a lower bound for x. So in this case, the largest integer that is a lower bound for 2.1 would be 2. And I'll zoom in a little bit so it's easier to read. Okay, what about the floor of -1/2? Okay. So if we think about between what two integers is -1/2 found, well, it's found between -1 and 0. Right? This is -1/2 right there. So the largest integer that is a lower bound for -1/2 would be this -1. Let's see, for the value 0.06, the floor of 0.06 is going to be 0. Again, because 0.06 is found between 0 and 1. So 0.06 is going to be somewhere in this region. So largest integer that is a lower bound for x would be 0. And then finally, the floor of -8 would simply be -8, because the floor of any integer will be the integer itself, according to this definition. Now the seating function is very similar, except that we're going to be rounding up instead of down. And again, that rounding up is going to occur regardless of what the decimal value is. So if I take the ceiling of 2.1, that'll be a 3, because I am now looking at what is the smallest integer that is an upper bound for the given value. And so this is 2, this is 3, 2.1 lives here. The upper bound, or the smallest integer that is an upper bound for 2.1 would be 3. The ceiling for -1/2 again, if we refer back to our little number line that we drew up in the previous example, -1/2 is found between -1 and 0. So that means that the upper bound for it would be 0. The floor for 0.06 would be 1, because 0.06 is found between 0 and 1. So now we take the next integer. And the ceiling of -8 would still just be -8. And that is because, according to our definition, the ceiling of any real number x is going to be n plus 1, where n plus 1 is the next integer with the possibility that x is that integer. Okay, so in this case, we have it's -8. All right, so those are ceiling and floor. We're going to be graphing those functions, starting by graphing the floor of x. Now, just like you would, well, actually, let's take care of the integers, because those are pretty easy to calculate. The floor of it's simply going to be the integer itself, right? So if I take the floor of 0, I'm going to get an answer of 0. If I take the floor of 1, I'm going to get 1. If I take the floor of 2, it's 2. Of 3, it's 3. Of 4, it's 4. So on and so forth. And so we're going to have all those points part of the graph. And now I want to find out what happens in between those values. So what happens between like 0 and 1. So I'm just going to draw a table here to help me keep track of my x values and y values. And I'll add some more rows as they become necessary. Okay. So let's see. If I consider, let's just choose like say 1/2. Okay. If I take the floor of 1/2, it's going to be 0, which means that I'm going to end up at 1/2, 0. If I take 3/4 or 3/4, and I take the floor of that, the floor is also going to be 0, right? So in fact, any number between 0 and 1, including the 0 and excluding the 1, any number in that range, any x value, is going to get mapped to the y value of 0, meaning I'm going to have this situation. And then at 1, I'm going to draw an open circle, because at 1, we know that the floor of 1 jumps up to 1. Okay, so we end up with that point. Now, what happens between 1 and 2? So again, if I take, like, let's say the value 1.5, and the floor of 1.5 would be just 1, right? So I would have this point here. Basically, anything between 1 and 2, including the 1 but excluding the 2, will get mapped to 1. Okay, so we're going to have this situation with an open circle at 2, because when first of all, I'm not including it as part of the range here, but if I were to plug in a 2, the floor of 2 is 2. So it jumps up to this next point. And so we just kind of repeat that idea. Now if I consider from 2 to 3, all of those values like 2.1, 2.2, 2.5, 2.9, those are all going to get mapped to 2. And so these values between 2 and 3 get mapped to 2. And then at 3, we jump up to 3. Then between 3 and 4, they all get mapped to y value of 3. And at 4, it jumps up to 4. Okay. So that would be in the case of the positive numbers. In the case of the negative numbers, I'll draw some more rows to consider those ranges. So let's consider the range from -1 to 0. Okay, so from -1 to 0, let's see what happens. Well, at -1, I know that I get -1. So actually, I'll erase these, and then we'll try to determine what the correct parenthesis or bracket should be. But if I have a value, let's say like -1/2, that's going to get mapped to 0. So I'm going to get this point. If I have -3/4, that's still going to get mapped to, oh, actually, excuse me. I have that wrong. If I have a -1/2, a -1/2, I'm thinking ceiling at the moment, we're still on floor. So if we're looking at the floor of -1/2, -1/2, which we found in the previous example, that was -1, right? So I'm going to get mapped down to -1. If I take the floor of -3/4, that is also going to get mapped to -1, because that is the largest integer that is a lower bound for that number. So basically, anything from -1 to 0 is going to get mapped to -1. Okay, so I'm going to end up with this. And then anything from -2 to -1 is going to get mapped down to -2. Okay, so it's going to have this straight line. Anything between -3 and -2 is going to get mapped down to -3. And anything between -4 and -3 is going to get mapped down to -4. And if you're a little confused as to why that is, again, you can just check by plugging in some values. If I try to find the floor of -3.5, that is asking between what two numbers, between what two integers does -3.5 live. So this would be -3.5, -3 would be here, -4 would be there on the number line. And I want to take the smallest of the two integers that bound -3.5, so it would be that -4. So this here would be -4. And that means that the floor of -3.5 is -4, which is down here. Right. Now the ceiling function is going to be a similar process. For the ceiling function, again, the integers are still getting mapped to themselves. So like 0 gets mapped to 0 because the ceiling of 0 is 0. The ceiling of 1 is 1. The ceiling of 2 is 2. And these points will look exactly the same as they did for the floor function. But now when we start considering other places, other numbers, so if I consider let's say like 1/2, the ceiling of 1/2 is now going to be 1, right? Because we want to find an upper bound, or the smallest upper bound for 1/2, that is an integer, so it would get mapped to this point. If I take the ceiling of 3/4, that is also going to be 1. Yes, I'm going to have a point there. And anything between 0 and 1, including the 1 but excluding the 0, is going to get mapped to 1. Anything between 1 and 2, excluding the 1, including the 2, is going to get mapped to 2. And so I invite you to verify that that is the case by attempting some actual numbers. Okay, but the graph for the ceiling function will look like this. It looks like a step function. All right. So here's a little bit of an application for those ceiling and floor functions. So data stored in a computer disk or transmitted over a data network are usually represented as a string of bytes, and each byte is made up of 8 bits. How many bytes are required to encode 100 bits of data? And so, all right, so just to reiterate here, they're telling us that 1 byte is equal to 8 bits, and that's our given. And we want to know how many bytes are necessary to encode 100 bits of data. So we could simply do, we can simply say, well, if I take 100 and divide by 8, so that is the number of bits, and this is the number of bits per byte, so that in the end of this computation, I should get number of bytes, right? Because my bits are going to cancel out, and I have 1 over byte. I have 1 over byte, so I would end up with bytes. And so I'm going to get, if I punch it into my calculator, I'm going to get a decimal, obviously. So this is 12.5. Okay, 12.5 bytes. But the thing is, when it comes to, a computer disk, there's no such thing as a half a byte. So instead, what we have to do is we need to think about, well, if I have 12 and a half, that means that I would actually need to have 13, right? I would need to have 13 bytes to accommodate for all 100 bits. Yeah, so we take the ceiling of that. Here's another application. So in asynchronous transfer mode, data is organized into cells of 53 bytes. And they're asking us how many ATM cells can be transmitted in 1 minute over a connection that transmits the data at a rate of 500 kilobits per second. Yes, again, we're going to try to organize what is given versus what is it that we want. So we're given a rate. Okay, would they give us a rate of 500 kilobits per second? That's 500,000 bits per second. So that's one thing. They also tell us that data is organized into cell of 53 bytes. Okay, so they tell us that one cell is 53 bytes. Or we can also think about it as 53 bytes per cell. And the goal of this is to find out how many cells we can transmit over 1 minute. Okay, so we want to know how many cells per minute. All right, so the first thing that we want to do is we want to make sure that we have the wanted units for both of these given. So I'm going to change this bits per second into bits per minute. And so now here comes a little bit of my work. Okay, so the rate is going to be 500,000 bits per 1 second multiplied by 60 seconds per 1 minute, so that my seconds are canceled out. And I'm going to end up with 30 million bits per minute. Okay. And then what? Well, then we want to find out how many, instead of having bytes per cell, I want to transfer, or I want to translate it into how many bits per cell. So then that means that I have 53 bytes per 1 cell multiplied by, we have 8 bits for every byte. Or in other words, we're going to end up with 424 bits per cell. All right, so now we have the units that are required in the goal mean, how many cells per minute. Let me just take out a sticky note so that I can continue to work there because I've run out of space. All right, so in order to get cells per minute, I would need to take my rate of 30,000, sorry, not 30,000, 30 million bits per 1 minute. Actually, let me just write it here. I think that'll be okay. Divided by 424 bits per cell. And now, why am I doing that? Well, because then what's going to happen is that my bits are going to cancel out. And then since this can be counted as a 1/1 cell, okay, for the units, then the units are actually going to end up with cell being in the numerator. And then this is a 1/minute, so we'll end up with cells over minute. Okay. Now what we have to be careful about here, though, is that this, I'm saying, is going to give me the cells per minute, but remember, this is likely going to give us a decimal. Okay, this doesn't look like it's going to divide nicely. So in order for me to be careful about that, I want to find out how many whole cells are going to be transferred over ATM. So I'm going to take the floor so that I can find out how many whole cells, not any fraction of a cell, are going to be transmitted in 1 minute. Okay, so I'll write here the number of whole cells transmitted is going to be the floor of this computation. Okay, so if you punch it in your calculator, we're going to get approximately, let me see, we're going to have 30 million divided by 424. So that's going to be the floor of 70,754.72 approximately. So it's just going to be 70,754 cells per minute. And so that would be the rate. And that means that in 1 minute, I'm going to have 70,754 cells. These problems are really just unit problems more than anything. Okay, the floor comes into play, and the ceiling comes into play, but I think the trickier part is just getting the units correct. All right, and then number 6, I'm going to skip over simply because this is more of a proof problem. I'll give you a hint though, because we have solved this type of problem before. So example number 6 is to prove that the floor of 2x is equal to the floor of x plus the floor of x plus a half. So the hint for this is to solve by using a proof by cases. Okay, so this one, I'll just say proof by cases. And I believe in proofs part 1 is where we completed an example that was very similar to this. Okay, so I'm going to ask you guys to look at proofs part 1. It's 1 or 2? Let's see, I think it's 2. If it's different, I'll change it before I scan and upload to Beachboard. We're going to skip over that one, as well as the next example. That one's also a proof, and then well, actually that's short enough that I can complete it. Let me just go ahead and complete it because it's actually, they ask us to prove or disprove. So prove or disprove that the ceiling of x plus y is equal to the ceiling of x plus the ceiling of y for any two real numbers. And so we can easily prove that or disprove that with just by considering some numbers. So like consider maybe x is equal to 3.5 and y is equal, let's say, to like 1.5. If I take the ceiling of x plus y, that is the ceiling of 5, which is simply going to be 5. But if I then take the ceiling of x plus the ceiling of y, that is going to be the ceiling of 3.5 plus the ceiling of 1.5. It's 4 plus 2, which is 6. Okay, so here we can see that they are not equal. And so really anything that, yeah, I mean, that's one counterexample, but you can find plenty of others. So that one did not work out. What about the next definition, factorial? Okay, so factorial function is a function that maps from the natural numbers to the positive numbers and is defined to be as n multiplied with n minus 1 multiplied with all the way down to 2 times 1. Okay. And then there's another part, second part of the definition. The only exception to this rule is that when you have 0 factorial, that is not 0. Rather, 0 factorial is defined to be 1. Okay. And factorial is defined with, is denoted with this exclamation mark. Okay, so it looks a little funny, but that's factorial. So let's see. We want to find out what is a factorial when a is equal to 3. So f of 3 being 3 factorial means we're simply taking 3 times 2 times 1, which is 6. Then if we want to take 6 factorial, that would be a 6 times a 5 times a 4 times a 3 factorial, which we've already computed over here. So that would be, let's see, this 6 times 5 is 30, times 4 is going to give us a 120. So it's a 120 times a 6, because I've already found 3 factorial to be 6. So this is simply a 720. And finally, f of 20 means we're trying to compute 20 factorial. And that is going to be an extremely large number. So we might want to rely on technology to help us with that. It's not something that's practical to do by hand. So if you have a graphing calculator or calculator similar to this where you can access the catalog, what you can do is you can type 20 and then access the catalog and look for the factorial symbol. So in my case, I just have to keep scrolling up or going up and I guess scrolling down. And then I'll find the factorial symbol right after Z-trig. Yeah, so I'm going to use it there. And it's telling me it's something like 2.4329 times 10 to the 18. So it's a very large number. I'm going to approximate it here instead of writing what it actually is. I'm going to say it's approximately 2.43 times 10 to the 18. The factorial is actually a function that grows quite quickly. Okay. Now, one more definition, and that is a definition of partial function and domain of definition. So we're going to be considering 3 sets, A tilde, and B. And we have the condition that A tilde is a subset of A. So basically what we're looking at is a set A with a subset A tilde and a subset B. And then we have a partial function f from A to B is a function defining an assignment of a unique element in B to each element in A tilde only. That is, f is only defined over the elements in A tilde and undefined everywhere else in the domain of A. So basically, we only have elements from A tilde getting assigned to a unique or to one element in B. And that A tilde subset is called the domain of definition. Okay. So here's an example. If you have this function that maps from the integers to the real numbers and it's defined by the square root of n, okay, so you're plugging in an integer, taking out a real number, that's considered to be a partial function because you cannot take the square root of negative integers. So that means that we would only be, so our domain would be the integers, but our domain of definition would only be the positive integers are 0. So that would actually be the natural numbers. Okay. So the set of non-negative integers. All right. Okay, so those are some important functions to keep in mind. We're now going to take a look at the applications of these, or some more applications, because we did take a look at two with the floor and ceiling functions. But one main application that you guys are going to see again in 328 is that of analyzing algorithm efficiency. Okay, so when we're thinking about how to describe how well an algorithm performs, we want to develop a language that allows us to describe that. So when we think about efficiency, what is it exactly that we think efficient means, or the word efficient means? Well, I think that the majority of us immediately think about how quickly can it perform the desired computation, or the desired number of steps. So that is in part, correct. When we think of efficiency of an algorithm, we think about how quickly can it compute it, but we don't think about it in terms of time, and here's why. One algorithm with the same number of steps, the same implementation, might run very differently depending on the hardware of a computer. So it might run very differently from my laptop to a computer in the lab, say. So we don't want to define efficiency in terms of time, because time is going to be different for different computers, and then it's going to be based on the same algorithm. So instead, what we want to think about is, think of the number of steps, or think of the number of visits that are made in order for an algorithm to execute. So here's an example. Let's say that you have this procedure of finding the max of some given n elements. And we start off by defining, well, the max is the first element, even though it may not be, but for now we're saying that is the max. From there, we iterate through the rest of the elements and compare their value versus what we currently believe is the maximum value. So for I equals 2 to n, if the maximum is less than the current value that we're considering, then we're going to update the max to be the current value, and then finally return the max. So let's see. If we think of efficiency in terms of how many computations this algorithm is computing, well, there is one computation here because there is a comparison. And by computation, I mean things such as, let me be very specific about this. When we say computations, and we're thinking along the lines of comparisons, we're thinking about addition, multiplication, division, subtraction, integer division, modulo. And so those sorts of computations, assignments are sometimes or usually ignored when it comes to counting the number of computations. So that's why I'm not counting this as a computation, the assignment of A1 to max or the assignment of AI to max. Okay, we just worry about either comparisons or one of these computations. So let's see, how many computations are necessary? Well, first of all, there's this comparison, and that comparison happens for I being 2, 3, all the way to n. So there are n minus 1 comparisons. Or n minus 1 comparisons. Some people also like to think instead of computations, they like to consider efficiency in terms of the number of visits that are made. Okay, so if we think about visits, so this was for computations. Okay. The number of visits that are made, well, we visit the first element to assign it to be max, so we have 1 plus, and then we compare the ith element for I is 2 to n, so that would be n minus 1 visits to A2, A3, all the way down to AN. So that brings us to n visits to the element. So which one of these do we pick for the efficiency? Okay. All right, so we're going to be then talking about how this number of visits or number of computations relates to the runtime. So let's say that computer 1 takes 1 nanosecond per computation, while computer 2 takes 10 nanoseconds per computation. So what would the runtimes be if we had these array sizes? Okay, so just to make our computations a little bit simpler, if I consider the number of computations for that algorithm, we said the number of computations was going to be n minus 1, right? Because we had n minus 1 comparisons. Now, if the array size is extremely large, like in this case, this is a 10 to the 9, okay? Then the number of computations, which is n minus 1, this minus 1 is going to be negligible compared to the size of n, meaning it's not really going to have an effect. Okay, so when n is very large, this is approximately n. Okay. All right, so what I'll do then to find the runtime, I'm going to take the number of computations, which is approximately n, so that's going to be 10 to the 9, and I'm going to multiply by the rate. How many seconds per computation does the computer take? So for computer 1, they tell us it's 1 times 10 to the minus 9 seconds per computation, so that's 10 to the minus 9, and that'll be 1 second. Now I'm not writing the units here just because I don't have enough room, but this is like 10 to the 9 computations multiplied with 10 to the minus 9 seconds per computation, so I have seconds as a remaining unit. Now in this case, I have 10 to the 12, right? Yeah, I have 10 to the 12 computations. So that means that my runtime is going to be 10 to the 12 times 10 to the minus 9, or in other words, 10 to the third seconds, 1,000 seconds. When it's 10 to the 15, a size 10 to the 15, then my number of computations is approximately the same as the size. So I'll have 10 to the 15 computations multiplied with a 10 to the minus 9. which is going to be a 10 to the 6 seconds. What about for computer 2? For computer 2, we'll have, again, the size multiplied by the rate for computer 2. So for C2, it takes 10 nanoseconds per computation. So this was for computer 1. For computer 2, it's 10 times 10 to the minus 9 seconds per computation. Or in other words, that is the same thing as 10 to the minus 8, right? Because this is like 10 to the 1. 1 minus 9 is negative 8. So it's 10 to the negative 8 seconds per computation. So it's a little bit faster. Just kidding, it's a little bit slower. It takes a little bit more time. So we're going to have 10 to the minus 8 multiplied with the number of computations, which is approximately 10 to the 9. So we're going to take about 10 seconds on computer 2 to execute that algorithm. 10 to the 12 computations times 10 to the minus 8 computations per second results in 10 to the 4 seconds for runtime, and then 10 to the 15 times 10 to the negative 8 is going to give us 10 to the 7 seconds for computer number 2. So the difference between how fast computer 1 runs versus computer 2 is a difference of a factor of 10, right? 1 times 10 gives me 10 seconds, 10 to the 3rd times 10 is 10 to the 4th, 10 to the 6th times 10 is 10 to the 7th. There's a factor of 10. But if you consider just the computer with itself, compared with itself, its runtimes, so with 10 to the 9, it was 1 second. With 10 to the 12 is 10 to the 3rd. 10 to the 15, runtime is 10 to the 6 seconds. This is just growing like a constant times the number of computations, meaning I'm taking this size and multiplying by a constant. In this case, the constant is 10 to the minus 9. Similarly, when on computer 2, I'm just taking the size, multiplying by a constant to get the runtime. And so the size multiplied by constant. So for both of these computers, we can say that the algorithm, how fast the algorithm runs, is going to behave like a constant times the size of the array that we're running the algorithm on. So we can say that the efficiency is approximately a constant times n. Okay, so when it comes to considering how good or how bad an algorithm is, we don't care too much about the exact runtime. We care about the overall behavior as we take n to be very large, meaning as we consider the data size to be very large, how do the number of computations behave relative to the size n? And so that brings us to the definition of big O. And let f be a function from a set A to the real numbers, and g be another function from the same set A to the real numbers. Then we say that f of x is big O of g of x if there are constants c and k such that the absolute value of f of x is less than or equal to a constant times the absolute value of g of x whenever x is greater than k. So this is a little bit difficult to digest. I want to break it down a little bit before we attempt any of the examples. Okay. So I want to break it down by reminding you of what it means to have absolute value. Okay, so let me just write here on a side note. So recall that if you have the absolute value of x is less than or equal to, say, 3. Okay? Just an example. What that means is all of the numbers, this is read as what are all the numbers that have a distance of 3 or less from 0, right? So absolute value is just the distance. So that meant that x could either be any number that is less than 3 but greater than -3. Any number in that range will satisfy this condition. Okay. Again, that is simply because we have, this is x, and this is 3, and this is -3. Sorry, this is 0, not x. Then any number that is found between 0 or 3, or any number that is found between 0 and -3 is going to have a distance of at most 3 from 0. Okay. So when it comes to now having absolute value of, say, and again, I'm going to go in steps. So let's say that we have absolute value of a function f of x is less than or equal to some constant, let's say c. And what does that say? Well, then that would mean that f of x is bounded above by some constant, c, and bounded below by negative of that constant, c. Okay. And let's say we are saying, well, that happens whenever x is greater than k. Okay, so when x is greater than some constant k. So again, what does that mean? Well, if I were to draw a graph of potentially what can satisfy those conditions, right, so let's say I have this being c and this being -c, and I'll say that this is k. So what this is saying is that the function f of x has to be found between c and -c. It has to be found within the strip at all times when x is greater than k. So from this point on forward to the right, f of x is always going to be found bound between -c and c is going to be found in that strip. Whatever happens before k is uncertain. It may or may not stay within the strip. But after k, we know that it stays bounded between those two constant between those two values. Okay, so an example of a function that could satisfy that could be something like this. Like maybe we have something like that continues on in that direction. Okay, if this is f of x, then after k, after the value x is equal to k, it remains within that strip. It doesn't change. Okay, so there's some kind of asymptote that's forcing this f of x to stay in that area. All right, but that's not exactly what the definition says, is it? The definition says that f of x is bounded by a constant times absolute value of g of x. So let's see what that could mean. Considering that idea now, if we have the absolute value of f of x is less than or equal to a constant times the absolute value of g of x, that means that f of x has to be bound above by a constant times absolute value of g of x, and below by negative of that constant times absolute value of g of x. And they do say whenever x is greater than k. Okay, so when x is greater than k. All right, so what does that mean? Well, what that means is that we want to find some function that bounds or that is always going to have a greater value than f of x for x is greater than k, or a constant multiple of that value. So I think it's probably better if I show you this with with a graphing calculator. So I'm going to show you guys through Desmos an example of something that would satisfy this. So let's just consider, for instance, and then I'll go ahead and share my Desmos. Okay, so in this case, I want to consider this x squared in comparison to absolute value of x cubed. So absolute value of x cubed is this blue graph that you guys are seeing here. In fact, if I remove the x cubed, if I remove the absolute value, you guys can see that it's going to have, the usual kind of like, I don't know, kind of like, I'm looking at this and I'm thinking tangent. It kind of looks like this tangent graph for x cubed. Okay, so, and then x squared is this red graph that we have here. But I'm going to introduce back the absolute value because our definition for big O uses absolute value. So I just want to show you a comparison of two functions, x squared versus this one here. So if you guys notice, if I were to consider all of the x values greater than 1, okay, so when x is equal to 1, here I'm drawing this vertical line, for any value that is 1 or greater, strictly greater than 1, my absolute value of x cubed, this one here, is going to be greater than than x squared. It's going to be greater than x squared. Like for instance, if I take the value 2 versus 2 squared, well, that's going to be that point 2 comma 4, versus if I take 2 comma 2 cubed, which is just 8, I'm going to get something that is much higher. So this x cubed, or absolute value of x cubed, is going to be larger than x squared whenever we have x being greater than 1. So the way that I would express that would be the following. Let me come back to the dockhand. Okay, so the way that I would express that would be, well, x squared is less than or equal to absolute value of x cubed when x is greater than 1. The other thing I can say is that x squared is definitely also going to be greater than negative absolute value of x cubed, because x squared is positive always, and this is something that's negative. Negative times absolute value is always going to be negative. So this is for any value, right? But in particular when x is greater than 1 as well. So if I put these two statements together, I get that x squared is bounded below by negative absolute value of x cubed and above by absolute value of x cubed. So this here is the definition of big O. We would write this as x squared is big O of x cubed for our constant value c of c being 1, because this c value is whatever is in front of the absolute value, and in this case it would just be 1, and for k value of 1 as well, because this is our k value, and when x is greater than k. Now, in order to satisfy the definition, you only need to find one pair. Finding one pair of constants c and k is enough, but just because I found the constants 1 and 1, that doesn't mean that everyone else is going to come up with the same constants, c and k. Someone else might say, well, it's true that x squared is less than or equal to 2 times absolute value of x cubed, and it's going to be greater than negative 2 times absolute value of x cubed. So therefore, this also satisfies the big O definition with c being 2 and k being 1. What's important is that you find at least one pair of those constants. Here I'm just illustrating the definition. So in terms of the efficiency that we were considering for the algorithms, there isn't too much. This doesn't apply directly to the efficiency that we were thinking about, that I was talking about. But just like I showed that x squared is big O of x cubed, we're about to do an example in which we're going to show that x squared plus 2x plus 1 is big O of x squared. Okay? And so let's just say that the runtime for some algorithm was actually this n squared plus 2n plus 1. Okay, so it is like very precise runtime. But let's say that that runtime is specific for a computer. So let's say this is for my laptop. And then that, I mean, even though it's significant to me and my laptop, what exactly how long it's going to take, it's not very significant to anyone else because someone else might get something different. They might not get n squared plus 2n plus 1. Maybe they get n squared plus 4n plus 3 or something. So being this precise is not important. Rather, what we would like to think about is approximately how is it going to behave? What is the worst case scenario of my runtime? So what I would like to do is I would like to find some function, let's call it g of x or g of n since I'm using n here. We would like to find some function such that I can bound my runtime above by some constant times that function g of n. Okay? And so if I can bound it above by this g of n, and g of n is something that's simpler, that maybe doesn't have 3 terms, then I don't have to worry about being precise. I can just tell someone, like, hey, the runtime is bounded above by constant times g of n, bounded below by constant times, negative the constant times g of n. So the runtime is really just like big O of g of n. And here I'm kind of assuming that g of n is always going to be positive. That's why I've dropped the absolute value. But let's say that I pick some g of n that is positive, then I don't have to be precise about this. I'm pretty confident that everyone else's runtime is going to behave like some, in this case, we're going to see it's going to be like n squared. Okay? So let's attempt that example, example number 9. In example 9, I have show that f of x equal to x squared plus 2x plus 1 is big O of x squared. So let me just specify what is it that we want. We want to show there exists 2 constants, c and k, such that this function f of x is going to be bound by c times absolute value of x squared, but absolute value aren't going to be necessary because x squared is always non-negative, so I'm going to eventually drop those. And then it's going to be greater than or equal to negative c times absolute value of x squared. And this is whenever x is greater than k. So that's what we want to find out. What are those c and k that make this a true statement? Okay. So here's our work. All right. So what? So I have f of x is x squared plus 2x plus 1. I'm going to start by first trying to find something that bounds that above. So I want to see what that is less than or equal to. So notice this is going to be less than or equal to, and I'll write it here so that it lies directly, so that the terms align. That's going to be less than or equal to an x squared plus an x squared. I'll say, just so that it's a little clearer, plus an x times an x plus an x squared whenever x is greater than 2. Okay? Because when x is greater than 2, then x times x is going to be greater than 2x, or in other words, x squared is going to be greater than 2x. So that's what I'm doing with these two terms there. Okay, and then that is going to be especially true for these two terms, right? If x is greater than 2, then really anything x squared is going to be greater than 1 as soon as x is 2. So this could have been greater than or equal to 2 in that, for these two terms, but for these in particular, well, for those as well. I'm just trying to stay consistent with the strict inequality of the definition, but it could have been greater than or equal to 2 for either one of those pairs of terms. Okay, and then what is that? Well, if I simplify it, this is an x squared plus an x squared plus an x squared. That is a 3x squared. So far we've shown that x squared plus 2x plus 1 is less than or equal to a 3x squared whenever x is greater than 2. Now let's see, is it bounded below by negative 3x squared? Well, the answer is yes, because negative x squared is always positive. Negative 3 times something positive is going to be something negative. That is going to be greater than x squared plus 2x plus 1 when x is greater than 2, because this is going to be positive while this is going to be negative. All right, so this inequality is true because the sum of these terms will result in a positive answer, whereas the product of these two is going to be something negative. So hence what we've shown is that negative 3x squared is less than or equal to x squared plus 2x plus 1 is less than or equal to a 3x squared when x is greater than 2. Or in other words, that x squared plus 2x plus 1 absolute value is less than or equal to 3 times absolute value of x squared when x is greater than 2. So that is a definition of big O. That means x squared plus 2x plus 1 is going to be big O of x squared. And the key here being that we found the necessary constants C and K. C turned out to be 3 for our case, and K turned out to be 2. All right, so that's one example. Let's take a look at another example. Example 10. For example 10, we have to show that 7x squared is big O of x cubed. So what we want to show, again, let me just write what is it that we want versus what is it that, or, and then show the work, not versus. So if we want to show that 7x squared is big O of x cubed, we want to find constants C and K. Such that 7x squared will be less than or equal to that constant times absolute value of x cubed and greater than the constant c times absolute value of x cubed whenever x is greater than k. So let's give that a try. I'll start with the upper bound. So 7x squared, that is going to be less than or equal to an x times an x squared whenever x is greater than 7. So I'm simply, when you have this situation where your current function is pretty close to what you're trying to show is a big O of, so meaning your f of x is pretty close in degree to g of x, then sometimes it's useful to transform any constant that you might have into an x. Okay, so 7 times x squared is going to be less than or equal to x times x squared whenever x is greater than 7. So what that means is that 7x squared is going to be less than or equal to x cubed. Now, it is also true that negative, that's going to be greater than or equal to negative x cubed when x is greater than 7. Well, because this is going to be a negative answer, right? If I replace a positive number into x, in particular something that's greater than 7, and then I have negative of the result, that is going to be less than something that I plug into x here, because I'm going to get a positive answer. Okay? So therefore, what I have is absolute value of 7x squared is less than or equal to absolute value of x cubed. Okay? Or to be precise, it's less than or equal to x cubed, but I could also just write it's less than or equal to absolute value of x cubed because x is greater than 7. And when x is greater than 7, the x cubed and the absolute value of x cubed are the same thing. Okay? So as long as this is positive, these two are equal. So that is definition of big O. Here in this case, we have that our constant is 1 and our k value is 7. Okay, and one more definition. We have, one more example. We want to show that n squared is not big O of n. Okay, so how do we show that it is not big O of n? We're going to do it by contradiction. Okay, so we're going to say assume that they are. So assume n squared is big O of n. Then what that means is that there has to exist two constants, c and k. And there exist two constants such that when we take n squared absolute value, and absolute value is not going to matter too much because n squared is always positive. So it's going to be bounded above by a constant times n. Okay. Again, in this case, we don't do this greater than or equal to because n squared is always positive, so absolute value is the same thing as n squared. Okay. All right, so then, and this is when k is greater than, the other way around, when n is greater than k. Then what? Then, well, what would that mean? That would mean that 0 is less than or equal to Cn minus n squared. So remember, we're trying to prove by contradiction, so I'm trying to find a contradiction. So right now it's kind of like a trial and error sort of thing. I'm just manipulating this to see if I reach some kind of contradiction. Okay. So what that means is that I'm going to have, if I factor out the n, I'm going to have a c minus an n is greater than 0. N times c minus n is greater than 0. And that would mean that two possibilities. The first case is that n is greater than or equal to 0, and c minus n is greater than or equal to 0. Okay. Let's see if we reach contradiction there. Well, if one thing that I can conclude is that c minus n is greater than or equal to 0 by simplification. And then if I manipulate that so that I add n to both sides, I'm going to have that c is greater than or equal to n. So what this is saying is that n is bounded above by some constant c. Well, that is a contradiction. Okay, this is a contradiction because this is impossible. If you give me some value for k, all right, so let's suppose that k is 2, all right, then we have the condition that n has to be greater than 2, okay, and if you say like c is, let's say like 3, then because I can also, n, this n, by the way, or sorry, this big O of n, this is the function n. This is the one that looks like a straight line that grows without bound. So I guess that's probably a better description or a better explanation. If this is f of n is equal to n, okay, this grows without bound. It has no upper bound. I can place a lower bound on it. I can say k, okay, for n greater than k, but I can't place an upper bound on it because the moment that you give me an upper bound, like let's say, I don't know, 5, I can tell you, well, actually, for n being 8, I surpass that upper bound of 5. Okay, so this is impossible. Let me change the explanation here. This is impossible because f of n equal to n grows without bound. So hence, given any constant c, I can give you a value for n for which the function is going to be greater than c. Okay, so we can find a value n greater than k such that f of n will be greater than the constant. So that's not possible. So that means that case 1 is not possible. Well, what would be the other case? The other case, in order for this inequality to be true, the product of two factors giving me something that's non-negative, that means that they would have to be each individually negative so that their product can be positive or 0. Okay, so the second case would be that c is less than or equal to, n is less than or equal to 0, and c minus n is less than or equal to 0. Okay. Again, this is a contradiction. Okay, this is impossible. Because f of n is not bounded, yet this case requires that n be less than or equal to 0 at all times. If we're all n greater than k. So that's also a contradiction. Case 2 is not possible. So in other words, none of the cases are possible, which is a contradiction. Yeah, that's a contradiction. So then we have that n squared is not big O of n. Yeah, so usually when you're trying to prove that something is not big O of another function, you want to do it by contradiction. You want to start by assuming that they are, and then realizing that that leads to impossible cases. Okay, so here at the bottom of page 7, there is a graph with several functions. So there is this constant graph of 1. There is a graph for log n. There is a graph for n. And as you can see, this n looks a little funky because this is on a logarithmic scale. So it's going to flatten out a lot of these functions just so that they can all fit within, so that they're all comparable to each other within this window. And so what we can say from looking at these functions is that 1 is going to be big O of log n because it can be bounded above by log n. It could also be bounded above by n, or we could also say log n is big O of n, okay, because it's bounded above by n. And if it's bounded above by n, it can also be bounded below by n, because remember, or by absolute value of n, because it's not just by the function itself, it's by a constant multiple of that function. Okay, so if I multiply it by -1, okay, this n, I'm going to see something that looks, you know, in the opposite direction, going down depending on, well, actually it's going to be negative, but it's going to be bounding this log n below. Okay, so that, remember, it needs to be constant multiple of the function, negative constant multiple of the function below, and positive constant multiple of the function above. So n is bounded by, log n is bounded by n. We can say that n is bounded by n log n, and n log n is bounded by n squared by 2 to the n, and 2 to the n bounded by n factorial. And so this is what I was mentioning earlier, that n factorial grows large very quickly. It's actually one of the worst runtime. If you have something that has an n factorial runtime, it's likely you're going to be tossing that algorithm away because it's pretty much useless on any computer. Okay. All right, so that is all that I have for some important functions and applications of functions. I will be taking questions about today's lecture during Thursday's office hours, and we will also be addressing this on Thursday. Any questions that you might have at the beginning of class before we continue with the next set of lecture notes. Okay. So thank you for watching, and I'll hear you guys on Thursday.